Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about how to get the variance of a geometric random variable to be as such 1 minus p over p squared. And what is p? P is the probability of success. Okay. Now, in order to prove this, we need to understand what is geometric series, and then we need to be able to use this result, which is how can you find the sum of the second derivative of geometric series. So this is the formula to find the sum of the second derivative. And I'm just going to explain a little bit about this part before we go on proving that the variance is as such. Okay, right. Now let's say that we have a geometric series that looks like this. So we have the first number is a r to the power of 0, and then we have a r to the power of 1, sorry, a r to the power of 2 to the power of 3. So r here is the ratio, okay, and then a r to the power of 4, and then maybe, I don't know, a r to the power of 5, and a r to the power of 6, and maybe we can stop right there. Okay. Now, if this is your geometric series, you can simplify the process of finding the sum of the series. So that means you want to find the sum of it. So this is finding the sum of it. So sum of the series here can be represented as using the summation process, because this is obviously the process of adding up the terms. And you can see that the terms here are similar in nature, except that it has a difference at this point right here, which we can represent using, for example, notation x. So we have AR, and above here is x, where x is going to begin from 0 until n. So it goes on indefinitely, yeah? So that's how we can represent this long process into something that looks mathematically elegant and also saves space. Okay, so that's the whole thing. Now let's talk about the first derivative. Now let's talk about, okay, now we're just going to differentiate this stuff. So we're going to find the first derivative of this geometric series, and we're going to find the sum of it. So if you differentiate a r to the power of 0, the result here is definitely going to be 0, because r to the power of 0 is 1. So you differentiate this with respect to r, then the result is going to be 0. This one, the result here is going to be a. You differentiate this with respect to r, the result is going to be a. This one, the result here is going to be 2ar. This one, the result here is going to be 3ar squared. This one here is going to be 4ar cubed, and so on. And I hope you can see what's going on right here. So this is 5ar to the power of 4, and this one is 6ar to the power of 5, and it goes on. So what we have here is such a long process where you're going to add up all the first derivative of the geometric series. Okay, we're going to add all the values here. And how can we write that in terms of a precise notion that looks mathematically elegant? So we know that it has to involve this sigma notation, where it represents the process of summing up. And I hope you can see that the pattern given here, for example, this one, what happens is we have this value that is brought forward, and then this part here is reduced to something else, reduced by 1. So what happened here is actually, if we have ar to the power of 6, what happened here is 6 is brought forward, and then we have a and r, and then it becomes 5 here, because 6 minus 1 reduced to 1. And the same thing for this one. but you can see that 5 here, the value of 5 here is brought forward, so we have 5ar, and it becomes 4 because we have 5 minus 1. That's the process when you differentiate this term. So we can see that the term here is similar for every item. So we know that when you want to write it in terms of this formation, we have AR, so that one is going to remain unchanged. But what is different is we're going to have the value of x brought forward here, and r will be having x minus 1. The power here becomes x minus 1, right? You can see from here x will be brought forward, and the value here is going to be x minus 1. So that's what's going on here. We have this notation, x times ar, x minus 1. Okay, and x is going to begin from because here we have the value of 0, so x is going to start from 1. So x is going to start from 1, so 1 minus 1 is 0, so r to the power of 0 is 1. Okay, so we're going to start x from 1. We cannot have x from 0 because then it will be r negative 1, so that's not correct. So here we have x starting from 1 and until n. So that's what's going on, okay? Now let's talk about the second derivative. So if we have a second derivative of the geometric series here, of course, the result here is going to be equal to 0. This is a constant. If you differentiate it once again, it becomes 0. If you differentiate this result, this is a constant, it is also going to be 0. If you differentiate this, it becomes 2a. Differentiate this one, 2 will be brought forward, so it will become 6ar1, that means 2 minus 1. Next, 3 will be brought forward here, multiplied with 4, we've got 12ar squared, 3 minus 1 right here. Next, 4 will be brought forward here, so multiplied with 5, we got 20ar cubed. And finally 5 will be brought forward right here, so we have multiplied that with 6, we have 30ar to the power of 4. So I hope that you can see, if you want to represent this process in a concise manner, in a how do I say this, shorter version of the whole thing, here we can use a mathematical notation that applies sigma to represent the process of adding up. And here we can identify the process here is by having this value brought forward to be multiplied with this value. So in other words, we're going to brought forward this value to be multiplied with x. This value multiplied with this one. So x minus 1 will be brought forward multiplied with x right here. So we have x times x minus 1 ar, and right here is going to be x minus 1 minus 1. So you see that the exponent here is reduced because we have x minus 1 will be subtracted one more time, so we have right here is x minus 2. And of course x has to begin from 2 because when it is 2, then you have r to the power of 0 here until n. Okay, so you cannot have a negative value here, so x has to begin from 2. All right, next, of course, you can also see that if x is equal to 1, this part here is going to be 0, so really nothing much can be said about that. And similarly, if we put x equals starts from 0, then this one here will become 0, and not much can be said about it as well. So x has to begin from 1 for this one, and x has to begin from 2 for this one right here. Okay, Now just bear in mind this is the sum of the second derivative, and to get the sum of it we can apply this formula here, 2a over 1 minus r to the power of 3. Okay, now we are ready to show how to prove that the variance is given by this formula here. Of course, you're going to start off with, for example, variance of x. Everybody is familiar with this process, which is we got to find ex squared minus ex and you square it. However, in this case, for example, you can see that finding this is going to be a bit difficult, and so we're going to do a little bit of manipulation, which you have already seen in the binomial video. Instead of finding ex squared, we're going to find ex x minus 1 plus ex. This is what we're going to do. In order to find this value, we have to have this process. We need to find what it is. What is this one? Okay. Now, why are we doing this? I hope you can see that. This is x minus 1. This is a bit of a spatial notation, because why are we doing this has to do with the fact that we need something that looks like this, like x times x minus 1. That will make our life so much easier when you're trying to prove the variance of x is this one right here. Okay, right, so that's why we're doing that. We're doing that little manipulation because we need that. And I hope you can see what is this process. What is this green stuff right here? So this green stuff here is equal to x times x squared minus x plus ex, and this is equal to ex squared minus ex plus ex, and this can be cancelled out. Therefore, by doing this process, we will be able to get what we wanted in the original situation, which is we want this one. We want the value of this one, and in order to get this one, this is a process that we have to go through. We need to find what's the result of this. Okay. All right, so let's start with finding x minus 1, and the definition is that if you want to find the expected value of whatever function, we're just going to take that function and put it right next to our fx. So what is our fx? When x has a geometric distribution, fx is p1 minus p x minus 1. That's what we have learned in the previous video, and we know that x can take values such as 1, 2, 3, and so on. Okay, so we're going to define that right here. X can take value of 1 until n, and I'm just going to erase fx and replace that with the probability function. The probability function is p1 minus p x minus 1. Now, we can see clearly that if x is equal to 1, this term here is going to be 0. I mean, the whole thing here is going to be 0. Therefore, we can actually say that x can begin from 2. So when x begins from 2, then we have some result. For example, x, so 2 times 1 times p, blah, blah, blah. So we have a result instead of just 0. And I hope you can see that it looks similar to what we've got here. Looks similar, except that this part is similar. We have x is equal to 2. You can see we have x equals to 2 until end, and this part here is similar. but we got something right here and something right there, which looks a bit different to this guy and this guy, but it doesn't matter. This part here is x minus 2, whereas this one is x minus 1. Therefore, we need to do some modification again. Okay, so I'm going to focus on this part. Okay, so this part here, 1 minus p to the power of x minus 1, can be represented as something else. Okay, we can change the representation of it, and this is how we can change it. So here we've got x equals 2 until n, x minus 1 times p, 1 minus p. I'm going to change it so that it becomes x minus 2. So here I want to change it to become x minus 2 because I want to match with this one. Okay, here we got x minus 2. So if this is x minus 2, we cannot simply change it like that, because we need to make sure whatever changes here doesn't change the original expression. So that means we have 1 minus p x minus 2 times with 1 minus p. You need to add that 1. So the whole thing here is equal to this part. Okay, by the law of exponent, we know that 1 minus p x minus 2 times with 1 minus p, we can combine this process with equal to 1 minus p x minus 2 plus 1. So that becomes 1 minus p x minus 1, which is what's given by the original expression. Okay, so that's what I just did. Okay, so here I'm just going to write down very close next to it. So here we have some changes where this one here will be multiplied with 1 minus p. Okay, now in order to make it look very similar to this one, I'm going to rearrange what we have here again. So we're going to have something that looks like this. We're going to have n x equals 2 x minus 1. Now I'm going to consider p and 1 minus p together, very closely together, put it right next to each other, and then we're going to have 1 minus p x minus 2. I'm just rearranging the position of this expression, and I hope now you can see that it looks similar to what we have right here, to this one right here. Okay, and I hope you can see that a is equal to p1 minus p, that is a, and then r is equal to 1 minus p, and the whole thing here is the second derivative, the sum of second derivative of geometric series. So this is the second derivative of geometric series, the sum of it, and because of that we can apply the formula given here. Sum of the second derivative of geometric series is 2a. This is equal to 2a 1 minus r cubed. So what is a? A is this one, p1 minus p. How do you know that this is a? Because I have managed to represent this series to look exactly like this one. So I know that a here will be represented by p1 minus p. So that is a. So 2p 1 minus p. And what is r? R is this one right here, which is 1 minus p. So this is r, yeah? How do I know this is r? Because r is at this position with x minus 2. R to the power of x minus 2, yeah? So our r is 1 minus p. So 1 minus 1 minus p is going to be 1 minus 1 plus p. Okay? So 1 minus r is 1 minus this guy. So so it becomes 1 minus 1 plus p, because minus negative p is going to be plus p. And therefore, let me just erase this part. So therefore, what we have next is we can simplify that to be 2p 1 minus p over p, right? So that's what we have. And sorry, we have cube up here, so p cube. Okay, next we can simplify that to be 1 minus p over p squared. Okay, so that's the result for just this part, for just this one. Okay, and we are not done yet, because in order to find variance of x, in order to find ex squared, we need to do something else, some other process. So we're not done yet. Let's move on. So therefore, to find ex squared, we know that ex squared is similar to finding this plus ex. So this is going to be this guy. Okay, I'm going to write down this guy, 1 minus p squared. Okay, this one plus ex. Ex is 1 over p, and I've already shown how you can get 1 over p in the previous video, so I'm just going to use the result here. Ex, expected value of x, is 1 over p plus 1 over p. So that is ex squared. Therefore, variance of x is going to be this guy. Okay, so it's going to be the whole thing here, 1 minus p squared plus 1 over p. So that is ex squared. We have to minus ex and you square it. So minus ex, this is ex, and you square it. So that is variance of x. And now let's just simplify what we have on the right hand side of this equation. So we have 2 minus 2p over p squared plus 1p minus 1 over p squared. Next we have 2 over p squared minus 2 over p plus 1 over p minus 1 over p squared. So 2 over p squared minus 1 over p squared, the result is 1 over p squared. This one here, negative 2 over p plus 1 over p, is going to be negative 1 over p. And we can simplify that, and it becomes, here we've got p squared 1 minus p, right? So it becomes that. And if you want, can we simplify that anymore? No, I think that's what result is given here. So we have shown that the variance of x is equal to 1 minus p over p squared, and that's it. Okay, that's how you can prove it. And thank you very much for watching this video, and I'll see you again next time. Bye.